All right, so first, we're talking about adaptivity in the settings of unstructured meshes. And just to set notations, conforming refinement is typically what we do in simplex meshes. So if you have a mesh of triangles, for example, and you do bisection, you refine this triangle by introducing this edge here. I don't know if you can see here, this is dashed. That to ensure conformity, which means that you don't have faces that are a subset of faces in other elements, you have to introduce this forced refinement here, and then you continue the refinement. And you always guarantee that your faces are properly shared between two elements. Nonconforming refinement, in contrast, is natural for quadrilateral and hexahedral meshes. If you inform this conformity, in that case, you will get uniform refinement. So to get logo refinement, you don't inform conformity. You allow faces like this one that is a proper subset of another face, the coarse face on the right. And then you continue that way. What this introduces is degrees of freedom and vertices like this one, and like this one here, and like this one. They're called slave nodes or slave vertices. OK, so I'm going to start by telling you about the approach we have in MFEM for unstructured adaptive mesh refinement. And then we will switch again, and Mark will tell you about some work in PUMI for integration with MFEM. My focus will be on the non-conforming part. We do have some conforming mesh refinement in MFEM too. But for this particular talk, I think the non-conforming part is probably more interesting. Here are just two examples of unstructured non-conforming mesh refinement. I'm going to show you this example. And this is the map of Australia with one of the mini apps we have generated with one of the mini apps we have in MFEM. Okay, for the purposes of this talk, the methods we have in MFEM are H refinement with fixed P. If you're familiar with HP refinement, you know what that means. So we're not doing full HP. We're fixing the polynomial order and just refining the mesh. Okay, with that though, everything else is pretty general. We support any order mesh, any order space, the whole DRAM complex that I talked about earlier. In 2D and 3D, the order of the hanging nodes, so how many times you refine on one end, is arbitrary. There's no restriction that we've only refined once. There is support for anisotropic refinement. We already heard that's very important. There's also support for derefinement, which means coarsening elements. As you refine in certain areas, you want to derefine in others. And this is all serial in parallel with parallel load balancing. This means when you refine in parallel settings on certain processors and you get many more elements in one processor than in the other, you reshuffle the elements so everybody has about the same amount of elements. As I mentioned earlier, the goal here is that this is independent of the physics, so it's easy to implement and incorporate in many applications. OK, just to give you a flavor if you're not familiar with non-conforming meshes and slave nodes, this is what you have to do. If you have a mesh like this and you're interested in defining an H1, which means continuous finite element space, the value at this node C here is not independent, but instead is derived from the values in nodes A and B. Since on the coarse element we have, for example, a linear function here, C is constrained to be the average of the values at A and B. And this is called a slave node. This was a pretty simple case. But if you have more interesting spaces, for example, H curl, where the degrees of freedom are associated with the edges, then what happens is that these red edges become slaves of the edge D, and the constraint here is that they're half of the value at D. This actually depends on the orientation, but assuming they match orientation. So in general, this is what happens here. When you always when you have a coarse-fine interface, the fine degrees of freedom on the coarse-fine interface are slaved to the coarse degrees of freedom on that interface. Okay, because the coarse is you can't have both of them to be true, and the coarse is the more general one. Things get even more complicated. You may have slave degrees of freedom that depend on something that we think it's their master, but the master themselves can be a slave. So in this particular case, this red degree of freedom here is slave to these three green degrees of freedom. And so all of this complexity, these are just simple pictures in 2D, but you can imagine in 3D it becomes even more complex. All of this complexity MFM hides behind an interpolation operator that just on a corresponding interface, and this also shows here how the methods, how the spaces, on a corresponding interface, it defines an interpolation operator. The slave degrees of freedom, the fine degrees of freedom on the corresponding interface depend a linear combination with some matrix of the coarse degrees of freedom. Okay? If you express this, if you assemble this matrix globally, you just get another interpolation matrix. This is very similar to what we did and what I showed you earlier when, about the way we approach parallel assembly. In that case, that matrix was very simple. In this case, this matrix incorporates the interpolation, so it has quite more complicated structure. But the end effect is the same. You assemble element by element to regular element stiffness matrix, and then you combine them together with this interpolation matrix P for variational restriction. And then you recover the solution. Just to give you an idea, so if you have a randomly refined mesh that looks, that's pretty nasty inside, you just assemble element by element, just as you will usually do, any bilinear form you want. Then you apply variational restriction, you solve, and you recover the solution with this P, and you recover a uniform continuous solution. All of this is done for you by MFM under the hood. You don't have to worry about it. You only define things locally element by element. Okay, so this is we alluded to this earlier, but this is a plot that shows you the benefits of adaptive mesh refinement. So it's on this 2D problem that kind of models a shock wave, and we're comparing uniform refinement. This is for first, second, fourth, and eighth order, and the error you get, the approximation error in H1, for a given number of degrees of freedom. Okay, that's on the x-axis. We're comparing that with what you get if you do adaptation. And adaptation in this particular case is it uses some anisotropic error estimator. As you can see, there's elements that are refined just in one direction. And as you can see, for a fixed number of degrees of freedom, you get much smaller error if you do adaptation. And in fact, the higher the order, the more that difference is. I mean, in this case, for example, if you're interested in errors, 2 digits of accuracy, you're much better using fourth order MR or eighth order MR. You just need, for the other methods, you don't even see how many degrees of freedom you need. But of course, this doesn't only work in 2D. This also works in much more complicated settings in 3D. Okay, this is an, as I said, we're developing this in MFM as a general library, discretization library feature, but this is what it looks like when you put it into a real application. This is this blast code that I mentioned earlier. It's a shock wave that propagates radially, and just to test the method, we propagate it through a randomly refined mesh. Okay? On the left here, it's 2-dimensional computation on 8 cores. On the right, it's 3-dimensional computation on 4,000 cores. And the thing that you want to see here is, first of all, you maintain symmetry, and you don't see any reflections that usually you have to be very careful. Oh. You have to be very careful about on the corresponding interfaces where you refined. So here is a video of this same problem that includes not just refinement, but adaptive refinement, as well as derefinement and parallel load rebalancing. So let me play this again. On the left here, you see the mesh, and you will see that some elements are refined in front of the shock wave, and some elements are derefined here. What you see on the right here are the domains. I think this was run on 16 processors. So you will see some domains look very small, but in fact, they encode a lot of elements. And these domains, I'll play it one more time. Sorry. And these domains are dynamically rebalanced as the computation is going on. How much time do I still have?
A total of 5 minutes.
Okay, all right. So since I have a little bit of time, I'd like to do a very quick demo. So again, these are the MFM examples. So just to show you what the different conforming and non-conforming refinement look like. And so this is a local refinement that is non-conforming refinement towards a point. And if you were to do this with the triangles, you will get a conforming mesh, which means that there are no slave nodes. And the mesh looks something like this. Okay? So this is just to give you an idea. Now I want to run one of the demos we have, example 15, which simulates refinement, derefinement, and load balancing. And I just want to show you how it works in real time. Okay, so what happens in this example is you have a series of shock waves that spread around, and I will stop it for a second. And what happens is we refine and derefine as this, the solution has low regularity where the shock waves are, and the solution is basically smooth here. So we refine and derefine as they pass through. And as we do that, we also rebalance the mesh. So let me show you the different regions. So these are 16, I think I ran with 16 cores. The different colors correspond to different processors. And as you can see, they give elements to each other, and they transition the data as the computation progresses. So let me. And so this keeps going. So this kind of happens automatically under the hood. This code is actually very similar to the first example that I showed. It just includes this additional rebalancing step. So I'm done.
Okay.
How expensive is this cell load rebalancing compared to the actual physics simulation of the code?
Compared to the actual physics, it's not that expensive, actually. But you still don't want to do it every time step, probably. You want the way we do it is you have a space filling curve, and you chop it up. So the balancing, the improved balancing is almost perfect. So you probably want to. It's up to you when you call that that function.
Actually, the slides I've got prepared don't talk that much about adaptation in comparison of conforming and non-conforming. So, but I can't resist to spend a couple of minutes talking about comparisons. A couple of comments. When you do adaptation with these types of meshes, you notice that the degree of anisotropy you can get, for example, where it's at 45 degrees, you can't get any anisotropy. And in a problem like this, you would really like exceedingly high anisotropy. So one of the advantages of more geometrically based conforming adaptation is you can get that higher anisotropy. A second issue that comes up is when your domains are general geometries and you start off with a coarse geometric approximation on your mesh, if you want to adapt and get to a better geometric approximation, that with these types of methods, often elements will turn inside out on you when you snap to the boundaries, or you're going to have strong limitations on them. So there's pros and cons to them. A final one is we found in a lot of fluids problems, when we have complex geometries, you have to start off with a fine enough mesh to begin with to start to capture some of the physics that you're looking for to adapt to. So in these particular methods, Zanyo said you can refine and de-refine, but you can't de-refine past the initial mesh. Whereas in the methods in the conforming mesh methods, because they're totally based on the same technologies used in the fully automatic mesh generation, you can coarsen as much as you want. So those are just some comparisons of the methodologies. Of course, there's prices to pay for you have a lot of extra work in the meshing. These meshes can be adapted almost, like that, where the mesh adaptation procedures that are conforming, that really deal fully with the geometry, are going to be more time consuming. So let me jump to the slides I wanted to talk about. So I want to emphasize geometry aspects. This morning I had to explain the tools that have been developing FastMath quite quickly, and I wasn't able to emphasize what I think is some fairly important things, in that we're really looking at, when we develop these interfaces to analysis codes such as MFEM, that one can really do automated analysis. And by my definition of automated analysis, I'm talking about starting with a CAD model or image data with all the analysis attribute information, the boundary conditions, initial conditions, material properties, your loadings, defined in terms of that CAD model. No mesh exists. You press the button, and that one I want to be automated from that point on. So you really need to start with a complete understanding of the domain, your parameters associated with it, and of course, what's your desired output in terms of fields and the accuracy you want for those. So in terms of some of the things you need for doing that, and things you have to be careful of, is that particularly with higher order methods, you have to remember that your geometric approximation, your finite elements, must be consistent at the boundary. And I'll show an example of that, an extreme example, but people don't believe that it's that important to take care of the geometry part of it. You must be able to, if you're going to be able to work with higher order methods, want to be able to generate fairly coarse meshes. That's actually a harder mesh generation problem than fine meshes. Fine meshes are much easier to generate than very coarse meshes. Right? We also need curved mesh adaptation within that. You need to have all these things interact with the geometry as you're moving forward. And the geometry can come from multiple sources. So within the methodologies, we're always maintaining, I'm not going to go into detail on this, but the relationship of your mesh to your original model, and we use the abstraction of topological representations as used in boundary model representations of geometries for doing that. Issues that are also important is your representation. Those little cartoons show how badly you can approximate a geometry of a portion of an ellipse with various orders of Lagrange polynomials by just doing pointwise fitting. By the way, most of the geometry methods used for higher order finite elements and that actually use interpolation points. Now, those are bad selections to begin with. If you use things like the Babushka-Chen points or whatever, you're going to get much better approximation. But there are alternatives. One that you'll hear a lot about in the finite element community is this isogeometric methodologies, which simply says you're going to use the same basis functions for your geometry and your mesh. There's nothing wrong with those, but in fact, it's not really necessary. And it doesn't eliminate the mesh generation problem as sometimes is advertised. You can also apply other geometric approximation methods we happen to be partial to Bézier polynomials just because they're fairly straightforward to work with. Their derivatives are Béziers. We tend to, you can use the rationals also, but in fact, we see no benefit to them. They make the computations much more complex, and you can control your order of approximation quite easily with just the Béziers, but you have various options, and you need to consider that when working with the higher order methods. So given those requirements, we are integrating the PUMI technologies with MFEM. So the key components of that, which were mentioned earlier, is the distributed mesh infrastructure for the conforming meshes, as well as the mesh adaptation, and it includes mesh motion in that, because for moving features, you would like to use mesh motion until you need to do topological modifications, and the dynamic load balancing must be part of that. And all that can be driven by an anisotropic mesh metric field. We've already saw on this slide, but just repeating in case anybody didn't see it earlier, the earlier presentation where you can get information on PUMI. So what is currently in place? We can generate initial meshes that are curved to begin with. There's some mesh generators that will actually do that. We use a particular one that will do quadratic meshes to begin with. Because we are in MFEM, you can go to certainly much higher order than quadratic. Can inflate the order of the geometry. At the moment, it's just up to 6th order, but it's with Bezier, so we can take it up to whatever order you want. You do start having a higher price with the higher order geometry. The tools can take either a straight-sided mesh or one that's already curved, like the quadratic meshes that we can get, and will inflate the geometry. This not only is to curve to the boundary, but because the curving to the boundary in itself can turn elements inside out, particularly when starting with straight-sided elements. It also includes the topological modification operations, basically tools from the mesh adaptation procedures. And all this can be managed in parallel. And I should mention the particular mesh generator that we use, you can actually generate the initial mesh in parallel. We've generated meshes of tens of billions of elements on 2,000 cores. So we're already bringing in meshes that are partitioned to 2,000 parts, right? So this is just the interaction. So we bring the mesh in from PUMI. Once we want to start doing adaptation of that, we need to keep the two-way links between the internal structures in MFEM and the PUMI to deal with the fields, because we do solution transfer during mesh adaptation on the fly as we're doing the adaptation. The reasons for doing the solution transfer with each mesh modification operation is it's much easier to deal with conservation requirements. For example, if I'm just refining an element, it's straightforward. I don't have to do any mesh-to-mesh mapping because I know exactly what I got. It's going to match entirely. If I'm going to do a coarsening, I know the portion of the mesh that's affected, and again, I can do the conservation with much less headaches looking around the mesh. The last few slides, I'm just going to emphasize issues of making sure you keep track of the geometry. So this is a fairly trivial geometry. If you bring in a coarse mesh to begin with and adapt without going back to the geometry, then of course you're going to be solving the wrong problem. With maintaining the geometry links, you can come in with a coarse initial mesh, and as you adapt, you improve your geometric approximation. In this case, just uniform refinement carried out. Importance of geometric approximation, we'll look at solving a rather trivial problem on a sphere in which we're using an exceedingly coarse mesh with just one internal node. So we wanted to have some solution even for the low order. So this is P equal 1 and a geometric approximation of 1. And there we're just stepping up in equal orders, which is what would make sense to do on this. The exact value is, and you can see you're converging quite nicely to the exact value for this. Now what happens if you leave a lousy geometric approximation and increase polynomial order? Well, you very quickly improve to a very lousy result on that. Sorry for the couple of numbers getting screwed up when the slide went from one machine to another. Now, a lot of people have said that, well, yeah, that's fine. The straight-side elements aren't good enough, but as soon as you get to a quadratic element, that's good enough. You take your polynomial order to whatever you want as long as you have quadratic geometric approximation. Well, you can see that if I go to P equal 8 and I only have a geometric approximation of 2, I'm a long way from getting the correct value on this problem. Now, of course, it's a very coarse mesh, but the point is that you need to keep the geometric order approximation so you can, you take that up, and you really should be increasing consistently as you go up in the order. And of course, these things do actually work for real geometry. So here's a real CAD geometry from an accelerator example. And a simple MFEM solution on this. The same one's been done in a P version code for full electromagnetics problems. And, I think it just about hit 0 just a second ago.
So are there any questions from our audience? Yes.
Yeah, you said that IGA doesn't get rid of the mesh generation.
That's correct.
I was elaborate more on that?
It's a long answer. Well, I'll make it somewhat short. You have to have a complete, consistent mapping between the parametric geometry of your finite element spaces and the parametric geometry of the object you're analyzing. CAD systems don't work that way. CAD systems start off and carry out Boolean operations. They trim surfaces. So you've got, if you look at a plate with a circular hole in it, they do a quarter of the plate. You see the nice isogeometric where they make it two four-sided regions. Well, that isn't how the CAD system works. You had a square, you subtracted a circle from it. The parametric space that exists is the parametric space of the original square, and they know what's carved out of it. So you don't really eliminate the mesh generation problem for real domains.
There's another question?
Okay. I just have a comment on that explanation. Can't you get patches and then just use extraction operators on whatever representation you get to get that mesh directly from it? If you get like a...
Do you want to write the software for doing that? I don't. And first, the CAD system, okay, so the finite element people are, the analysis people think they control things. The CAE industry has hit a $1 billion level, a yearly level of $1 billion. The CAD, computer-aided design, is like tens of billions. They're in charge. Them and the people that do the manufacturing. We serve them, right? So the systems that are used for design are what's going to be convenient for designers, not what's going to be convenient for doing finite element analysis. In addition, those meshes are going to be dictated by the geometry. I want my mesh to be dictated by the physics I'm solving. So if I've got a shock wave moving through something, I want to refine the mesh near that shock wave. I don't want to, in the middle of a domain, have a great big huge element, and now I have to go to P to 95 or something, right? So I don't want my mesh dictated by the geometry. And the CAD systems do not keep any parameterization of volumes. They only parameterize the surfaces.
So we'll take one more question before switching over. You've been waiting,
So how will mesh evolve if you have hydraulic instabilities, convections, or turbulence?
Okay, well, the mesh,
We're already on the next topic.
okay. One of the slides showed a dam break problem. It showed a couple of pictures of that. We started off with a wall of water here, and the water falls and goes over a thing. The mesh is following that, adapting as it goes along. It's all being done with coursing and refining. It's following that interface. Is that your question?
But if you have, for example, like cavern house instability, like a fluid is wandering,
Yep.
or if we have strong convection, the turbulence will
Well,
rise.
if you want to resolve it with DNS, if you want to resolve those things with directly in the mesh, this will follow that. I mean, I can show you blast problems where we have anisotropic meshes following the blast waves. It starts off and it coarsens and refines and follows it. That's not a particular problem.